All right, Raghu, are you ready?
I'm
Are
ready.
you here, I guess, is the first question. Okay, you're here.
Yeah. I'm here. Hold on. Let me actually check my camera once. Yeah, that's better. And where did my keynote go? Give me 1 second. Can I start sharing?
Please go ahead, yeah.
All right. Let's see where it go. Okay. You can see the slides.
Perfect, yeah, so next up we have Raghu Meka from UCLA, and he's going to tell us how much less is known about learning undirected Gaussian graphical models than everybody thought, and some partial answers that are very interesting. So go right ahead.
Hi,
Thanks,
Raghu.
guy.
Raghu, before you start, there's a build window in front of your screen. In front of
There's a what window?
a window of a build window. It says a building effects window.
In the
Right.
bottom right.
Oh, there it is. Okay, it's gone now.
Okay. Oh, I see. All right. I see it here. Perfect. Okay. Is it gone now?
Yeah, perfect.
All right. Okay. So, hello everybody. Today I'll talk about learning Gaussian graphical models, and it's kind of I'll tell you a little bit about what's known and what we do. And this is joint work with Jonathan Kellner, Freddie Kohler, and Ankur Moitra, all from MIT. So the talk has three parts. First, I'll talk about what GGMs are, the motivation for studying them, and then I'll talk about the special models, special cases that we'll study that arise in various learning applications, statistical physics, and so on. Then I'll tell our algorithm. It is very simple. The algorithm is encapsulated in just these two lines here. Then I'll say a few words about the analysis. Okay, and so what are Gaussian graphical models? So at the highest level, they're just any multivariate Gaussian distribution, right? So you have a multivariate Gaussian distribution with covariance sigma, and throughout this talk, I'll use the notation from statistics. Can you hear me? I got some weird message.
We can hear you.
Okay. All right, so, and P will denote the number of variables, right? So it's the underlying dimension of the space that we are working in. So our samples are always P-dimensional. Okay, and when we talk about GGMs, we're not talking about Gaussians, but we're talking about something else. So the focus in this area is on the precision matrix, which is defined as the inverse of the covariance matrix, and we'll use theta to denote the precision matrix throughout the talk. So why look at the precision matrix? And this goes back to this observation from 72 due to Dempster, who showed that the precision matrix encodes valuable information about the distribution. Not just numerical properties, but also something called the conditional independent structure of the distribution. So more concretely, suppose you have your precision matrix theta, which is sigma inverse, then the support of the precision matrix gives us the dependency graph. More concretely, suppose I build a graph where there are p vertices corresponding to each of the covariates, and add an edge between I and j if the corresponding entry in the precision matrix is non-zero, right? And Dempster showed that the distribution has the following Markov property with respect to this graph. If there is no edge between two vertices, I and j, in this graph, that is theta ij is 0, then xi and xj are independent, conditioned on the neighbors of a vertex I. So for example, here, 1 and 3 do not have an edge between them. So x1 and x3 are independent of each other when you condition on neighbors of 1, let's say 2 and 5. More generally, they'll be independent whenever you condition on any cut in the graph. So that's why we'll start looking at precision matrix. But another important thing that we'll do is looking at the precision matrix allows us to parameterize the complexity of the model differently. And this is important in the applications that we'll see. So we'll think of Gaussian graphical models or Gaussian distributions which are simple in the sense that their precision matrix has small degree. The dependency graph that comes out of the precision matrix has small degree. And we'll think of the degree as being much smaller than the underlying dimension. So the dependency graph is sparse. And this is the assumption that makes the formalism non-trivial and useful when viewing Gaussian distributions in terms of the precision matrix. Okay. So why look at this assumption and why look at this particular way of viewing Gaussian distributions? For one, this is actually very widely used to model statistical relations between various variables, especially when you think that there is a simpler dependency structure than just looking at covariances. And this is also used in concrete applications, for example, to model some networks that arise in biology and in other domains. So to give an example and to gain some intuition, this will be a running example throughout this talk. This is a very simple example where the algorithmic challenge that we look at is easy to solve, but it helps to keep this in mind. So the example I'll call it the random walk example. So here each xi is just the previous xi plus an independent Gaussian distribution, zi. So you have z1 through zp, which are IID normal, and then xi is xi minus 1 plus zi. The covariance of this distribution looks something like this. They are increasing from 1 through all the way up to the number p. It's pretty regular in structure, but remarkably, if you look at the precision matrix of this distribution, it's even nicer, right? So the precision matrix, the inverse of the covariance, is just this simple tridiagonal matrix with 2's on the diagonal and minus 1's on the off diagonal, the nearest off diagonal. And the dependency graph, as can be seen from kind of the equation that I wrote down earlier, is just a path, right? So xi is xi minus 1 plus zi. So given xi minus 1, every future xj would be independent of the past. And that's exactly the path graph. Okay? So let's keep that example in mind. And the main challenge that we'll address today is that of learning sparse GGMs. So I'm giving you samples from a Gaussian distribution under the assumption that the underlying precision matrix is sparse. And our goal is to approximately learn the distribution. To learn the distribution has two facets. One is structural learning, meaning I just want to learn the dependency graph of the distribution. And the other one is to do parameter learning. That is, not just learn the dependency graph, but to get some approximation for either the covariance matrix, the precision matrix, or in some other metric for the distribution. So today I'll mainly focus on structural learning. Often that is kind of the crux of the problem. If you can do structural learning, then implicitly you can reduce the dimension of the problem that you're working with and then solve all the parameter learning problems using standard techniques. So today I'll focus on structural learning. Meaning you're given samples x1 through xn. So n for us will denote the number of samples, and our goal is to learn the dependency graph of the Gaussian graphical model. And the challenge is that the number of samples that we'll see will be much less than the underlying dimension p. And we think it will be possible because we are making the assumption that the dependency graph is sparse. Each vertex has at most few edges d. And the quantitative bounds that we want are something like this. I'm going to assume that the degree is much less than p, so let's say little of p, and I want the dependency graph to have to be learnable with sample complexity which is much less than p again. Ideally, we want the number of samples to be logarithmic in the dimension. And the dependence on d could be, poly d or something as we see, but it's interesting even if you have something which is exponential in d. And as I said, learning the dependency graph is the core of the problem, and once we have that, we can learn parameters easily. And the ideal, of course, is to develop simple algorithms with provable guarantees, and that's what we'll strive toward. So let's go back to our example and look at a toy version of the problem. This I'll call unknown order random walk. So here there is some permutation pi, and I have the same model as before, but under this permutation. So x pi of I is x pi of I minus 1 plus an independent Gaussian zi. And the covariance matrix will be something, some jumbled matrix of the jumbled form of the previous covariance matrix. The precision matrix here is, looks a lot messier, but still it's sparse. Each row or column has only 3 non-zero entries. And the dependency graph for this particular one looks something like this. And the goal is you're not given any of this information. You're just given samples from this Gaussian. And you want to learn the hidden permutation. What are the least number of samples you need? How fast can you learn it? This already seems like a pretty interesting problem, even though we already know how to solve it. I think it's still interesting. Okay. So there's been a lot of work on learning Gaussian graphical models, especially there are these popular packages which are used in various domains. For example, when I was doing some literature search, I found that a lot of literature in psychology uses Glasso and Klein to learn to fit GGMs to the data that they have. Right. So let's look at what these methods show. Glasso is this work of Friedman, Hesti, and Tibshirani from 2008. And there have been subsequent papers analyzing it. And more or less, the best guarantee we know for this method is that it can learn GGMs with sample complexity that is d squared times log p. So the dependence on the dimension, underlying dimension p, is very good. It's only logarithmic. And the degree dependence is also pretty good. It's just quadratic. But the analysis require the GGM or the precision matrix to be incoherent, which is some kind of strong form of condition number assumption on the precision matrix. I won't define what it precisely means, but even for the simple case of random walk, this assumption is violated. And as we'll see, even for more generally, I think whenever you have long range correlations in your model, like if you have a path somewhere in your model, then the assumption would be violated. Similarly, there's this work of algorithm called Klein, Jitusai, Liu, and Luo from 2011. They have a guarantee that gets, again, logarithmic dependence on the dimension, but then they have a dependence on the maximum ratio of the entries in the covariance with respect to the precision matrix. So if I normalize the diagonal entries of the precision matrix to be 1, how big is an entry in your covariance matrix? And this is again some form of condition number assumption, and this is also violated by the random walk example. There, this ratio would be p, so the bound would be really bad. But again, whenever you have these kinds of paths embedded in your network, I think the assumption would be violated. Okay. So summary, we have these very nice methods, but they need some kind of well-conditionedness assumption on the precision matrix. And these are violated by simple models, and the assumptions are not even scale invariant under natural scalings. And as we'll see, it's not just that our analysis is falling short for these methods. As we'll see, they also fail empirically on a small variant of the random walk example. Okay. So, but before going ahead and trying to solve the problem, let's try to think what is even possible for this question. What can I solve information theoretically? If you put aside the complexity efficiency issues, how many samples do you need to learn a general GGM? And this, to formulate this precisely, I need to introduce one other parameter for the model. And this I'll call kappa. And kappa of theta, theta is the precision matrix, remember. It's, you look at any non-zero entry in your precision matrix and you try to check what's the signal strength on this edge. How big is this off-diagonal entry with respect to the two corresponding diagonal entries, right? So in some sense, this ratio theta ij divided by the square root of the corresponding diagonal entries theta I, theta jj measures the signal in just the 2 by 2 matrices corresponding to the edges. You're not looking at the whole matrix, just 2 by 2 submatrices. So this could be much smaller and nicer than, this could be much bigger and nicer than the whole, what happens when you look at the whole condition number of the matrix. And this very recent and very nice work of Mishra, Boufre, and Loco from 2018 showed that if you have any GGM is identifiable, the dependency graph is identifiable with sample complexity that is d log p by kappa squared. So the number of samples is logarithmic in the dimension, it depends on the degree is linear, and the dependence on this edge parameter kappa is 1 over kappa squared. And having some dependence on kappa seems very natural, right? You know, if the edge strength is very low, you should need many samples to even identify that there's an edge, even when you're looking at just the 2 by 2 case. And for the case of the random walk, the ratio kappa is just a half. If you look at the least off-diagonal entry, you just get half. And to complement this, there's an older work due to Wang, Wainwright, and Ramachandran from 2010, who showed that you need at least log p or kappa squared samples to learn the GGM. And this again makes sense because you need roughly 1 over kappa squared samples to notice that there is any correlation on any edge. And then, you know, if you have p dimensions, then you might need log p samples. Any questions so far? Please interrupt me if you have any questions. Okay. So this seems very good. I mean, it seems like the problem is completely solved, but there's one caveat. And this caveat is that this work of Mishra, Boufre, and Loco, the way it works essentially is to do some kind of brute force search on potential neighborhoods. So the runtime of the algorithm that they give is p to the O of d. So for each vertex, you look at all possible d neighborhoods and then check if that's the right neighborhood. So as a result, the runtime scales exponentially with the dimension. There's a question, in a situation where kappa is small, then it results about learning the part of the dependency graph on which kappa is large. That's a very good question actually. I don't know a concrete answer to that, even information theoretically. Part of the reason might be that when you do this kind of, you can't do like a brute force search and so on. So I'm not sure. That's a very good question. Any other questions? Okay, so hold on, how do I? Okay, so this dependence of p to the d is problematic even for moderate sized instances. You know, if you think of d is 10 and p is 100, that's already somewhat difficult to implement and run. So the question is, can we do better? Can we do better than possibly enumerating over all possible neighborhoods of a vertex, which we should think of as kind of what's possible by brute force search? So the concrete question now is, can I learn GGMs of degree much smaller than the dimension, and the number of samples is roughly d log p or kappa squared. The exact dependence on d and kappa could be worse. But I really want the runtime of the algorithm to be a fixed polynomial in p, something that doesn't grow with d. Can you even get p to the little o of d? That also seems not trivial. Okay. And the main result of this work is that this is actually true for a large class of models that people have looked at before. We can indeed achieve these goals. I'll talk about these classes in a little bit. There will be attractive models, symmetric diagonally dominant models, and more generally what I'll call walk summable models. Okay. And the main result will be that this simple greedy algorithm solves all of these ill-conditioned cases, and it also actually recovers the guarantees of Glasser and Klein when you have well-conditionedness. So it's kind of, you know, achieves the old results and gets these newer results for these potentially ill-conditioned models. Okay, so that's what I wanted to say about what GGMs are, the motivation for studying them, and what the results are. Now let me say a few words about the special cases that we'll study and the algorithm that we'll look at. So the first class of models we'll study are attractive GGMs. And a GGM we'll say is attractive if all covariances are non-negative. That is, any two variables are positively correlated or they're independent. Equivalently, if you look at the precision matrix, then the off diagonals in the precision matrix are all negative. That's when a model is attractive. And for example, there's this class of models called Gaussian free fields, which are essentially Laplacians on some graphs, which are as in statistical physics, and they are used for modeling Gaussian processes. They all belong to the class of attractive GGMs. The random walk model that we saw before is also an attractive GGM. I mean, the precision matrix was exactly this. The off-diagonal entries were just -1 or 0, so it's attractive. And even for attractive GGMs, if your models can be ill-conditioned if you have long paths. As I said, any time your graph has a path embedded in it somewhere, or something that looks like a path embedded in it somewhere, you get an ill-conditioned model. And so what was known even for learning attractive GGMs? Previously, there were no efficient algorithms. Again, efficient means runtime that is p to the little of t, something that beats enumerating all possible neighborhoods, with sample complexity that is logarithmic in the dimension p. And one of the results that we show is that there's a simple algorithm that I'll call a greedy prune, and we'll see in a little bit. And it learns attractive models with sample complexity that is d log p or kappa squared. So the dependence on p is logarithmic, the dependence on kappa is also right, 1 over kappa squared, and there's a multiplicator d in front. And the runtime is quadratic. And this is off from the information theoretical optimal sample complexity by a factor of d. So there's a lower bound for attractive GGMs as well, that you need at least log p or kappa squared samples. Okay, and so we'll get back to this algorithm and how to prove this later on. But let me now talk about a more general class of models, and the most general one that we looked at in this work, which are walk-summable Gaussian graphical models. So a GGM is walk-summable if doing the following operation on the precision matrix leaves the matrix still positive semi-definite. Concretely, suppose I have my precision matrix theta. Now I build a new matrix where I make every off-diagonal entry negative. So I replace every theta ij with negative minus absolute value of theta ij. Minus of absolute value theta ij. If the resulting matrix is still positive semi-definite, then we call the matrix walk-summable. And these were introduced by Malyoto, Johnson, and Wilsky in 2006. And these generalize many classes of models like attractive GGMs. If a model is attractive, all the off diagonals are negative, so doing this operation doesn't change it, so you remain positive semi-definite. There are things called pairwise normalizable, which also arise from statistical physics. They are walk-summable. Something called non-frustrated models, they are walk-summable. And there's something called symmetric diagonally dominant, which we'll look at later on, and they're also walk-summable. Okay, so this is the most general class that we look at, and they're actually well studied both in the context of GGMs as well as in other contexts in statistical physics. And the best previous result for learning walk-summable GGMs, it actually goes back even older than the work of Mr. Wu and Loco to Anand Kumar and others from 2012. Who gave an algorithm which runs walk-summable GGMs with logarithmically many samples, where runtime was again p to the O of d. And the second result that we have is that walk-summable models are actually learnable efficiently with quadratic runtime and dependence which is logarithmic in the dimension. The dependence on the degree d and kappa are polynomially worse off. You have d squared by kappa to the 6. We also give a more sort of sophisticated algorithm which kind of combines the greedy method that we have along with the standard optimization procedures, which gets d log p or kappa to the 4 dependence. But I won't talk about this hybrid method today. But I'll focus instead on the slightly worse sample complexity giving method, greedy prune. Okay. So now let me talk about the algorithm that we use. And this is kind of the greedy method that's been used very effectively for learning discrete graphical models, starting with the work of Bressler, and more recently with the work of Hamilton, Kohler, and Moitra, and also by Bressler, Kohler, and Moitra from, is there a question? Looks fine.
Yeah, it looks like there's a quick question that someone asked: is the dependence on kappa necessary for walk summable? So I guess that kappa to the fourth, whether it's optimal.
I don't think so. I think kappa squared is enough. It's just that I don't know how to do it.
You don't think there's a statistical computational gap there?
No. At least in terms of kappa, I don't know. I don't think so. At least for walk summable models, I think we should be able to get log p or kappa squared. Our methods inherently hit a bottleneck in that you cannot do kappa squared, but it would be surprising if there is a gap. Surprising to me.
Does this correspond to like fast and slow variance in lasso?
Yes, exactly. Yeah, but I'm not sure.
Are you leveraging like fast rate analysis in lasso?
I mean, actually, you can use fast rate here, but the bottleneck is not that. It shows up in how much improvement that we make. Like in the analysis, somewhere you have to show that when you add a vertex, you make some progress, and based on that, you need to get some accuracy in your solver. The solver is pretty good, but somehow in the analysis, the accuracy that you need for it to go through, that's off, I think.
Okay, cool. Thank you.
It's a good question. Okay, so let me go back here. So we had the similar greedy approach for discrete GMs. We're kind of following the same outline from what's been used with discrete graphical models. And the outline is something like this. You try to recover the neighborhood of each vertex in parallel. So, we're trying to learn the graph, but let me focus on a single vertex and trying to learn now the neighborhood of this single vertex and do it for each vertex in parallel. And the way we'll solve it for one vertex is the following. First, I'll build a candidate neighborhood set. I'll maybe grow it one vertex at a time until I hit some number of vertices. And along the way, I might have added some spurious vertices. So after I've done growing this neighborhood, I'll prune out some vertices. I'll look at which vertices are absolutely informational or absolutely contributing something and throw out the remaining. So this is the outline. So let's talk about how you do the second step. So how do we grow the neighborhood? So recall our input is a sample from a sparse GGM, and our output should be now we're focusing on designing a neighborhood for a single vertex, vertex 1. And the idea for us is the following. So we'll start with the empty set, and while the set S of vertices that we've added is small enough, we'll add the vertex that gives the maximum decrease in the conditional variance of x1. So in some sense, we are adding the vertex that gives us the max bang per buck in terms of explaining my current variance. So you just find the j, which minimizes our estimate for the conditional variance of x1 coupled with what we already saw and xj, and add that. And we repeat this until some budget. So this is similar to what's been done for discrete graphical models, but the potential is, I think, simpler here and different. And as it turns out, somewhat surprisingly, this method is actually equivalent, if you're familiar with the compressed sensing literature, minimizing this conditional variance is actually equivalent to orthogonal matching pursuit. You can build a sparse regression problem, and when you set up the language right, this greedy method is equivalent to running orthogonal matching pursuit. But we'll adopt the greedy terminology because it makes things cleaner and easier to analyze. Okay. So that's the growing a neighborhood phase. Next phase is to prune a neighborhood. And this is again simple enough. So you look at each vertex and you check, is it actually giving me some value? So if dropping this vertex doesn't hurt your conditional variance too much, you drop it. Okay. So for it to be eligible to be in the set, it should actually make a noticeable difference. And once again, you only have estimates, so you have to work with the estimates and not with the actual conditional variances. Okay, so that's the algorithm, and before talking about how to analyze it and what the precise results I've already mentioned, let me say a few words about some experiments. We actually did some experiments and some real-world graphs, which turned out to be walk-summable, but let me describe what happens when you have a toy example. So the simple challenge example is the following. I have the random walk example, just a simple path on half the vertices, and then remaining half I'm splitting into isolated 4x4 cliques. So the precision matrix is path plus cliques, the max degree is 3, and because of the path, this matrix, this precision matrix is ill-conditioned. So the bounds for lasso and climb do not apply here. And the precision matrix pictorially looks something like this. You have, this 4x4 blocks on the upper half, and then you have the drag diagonal matrix in the lower half. Okay. So what happens when you run all the methods? Something like this happens. You have lasso, climb, and greedy here. I'll finish the simulation. And if you look at the final outputs, you can see that greedy does remarkably well in recovering the graph, whereas climb and lasso have several spurious entries. And you can also see it in plots. This is the normalized error of the different methods. But more important is the following graph, which shows the number of samples you need to recover the graph. So if I change the intensity, the weight on the cliques of the edges of the clique, you can spoil the different methods' performance. So for instance, if the intensity was set to 0.95, then the sample complexity of climb seems to grow linearly. So the number of samples you need to recover the graph under pretty loose criteria seems to grow linearly with the dimension, whereas greedy prune does very well. And here actually when the intensity is 0.95, surprisingly lasso also does well. But on the other hand, if I change the intensity a little bit to 0.7, then suddenly lasso starts growing, whereas greedy prune still stays very good. And finally, there was this one method which I didn't talk about, but it's something that people proposed as a heuristic and implemented it. It's Menhausen-Bullman method. It's kind of a lasso based on Menhausen-Bullman estimator. It's kind of based on lasso. And on a simple random walk, it starts growing linearly, whereas greedy prune again works well. So in all of these methods, in all of these variations, greedy prune does well, but the existing methods do not seem to have logarithmic dependency for recovering the graph. Okay. So the summary, here are the main results. Greedy prune learns attractive models and gives walk-summable model and learns walk-summable models with somewhat similar but slightly worse quantitative parameters. And you can also recover the guarantees of lasso and climb under the assumptions that they were analyzed with. It's also empirically better. And one nice thing about our method, as well as even lasso and climb, is that even though everything I talked about was in terms of Gaussian distributions, there is a version of the problem which makes sense, which also works for non-Gaussian distributions. So suppose for some reason I know that I have some distribution which need not be Gaussian, but its precision matrix is sparse, and the distribution has good tails. Can I learn the precision matrix? And oops, hold on. The questions popped up now. I don't know why. There you go. Yeah. So if the distribution is non-Gaussian, we can still approximate the precision matrix as long as the precision matrix is sparse and the distribution has, polynomial or exponential or sub-Gaussian tails. Okay. So let me now, in the last few minutes, say a few words about the analysis of the algorithm for the two cases. So just to recall, we are trying to learn GGMs greedily. You have samples and then you're trying to output the dependency graph. These are the guarantees. But let me move on to the algorithm. So the analysis for attractive case is actually very simple and goes back to supermodularity of the conditional variance function. So we are fixing the vertex x1, and let me now define a function on the subsets of the remaining vertices. So f of s is the conditional variance of x1 given xs. And this is old result from 2006 and independently discovered in 2012, saying that if the matrix, if the Gaussian distribution is started out with is attractive, then this function f is supermodular. It's always monotonically decreasing, but when you have an attractive model, it's also supermodular. And why supermodularity just means that the net benefit of adding a vertex j to our existing set decreases as your set increases. And why is supermodularity useful? Well, optimizing supermodular functions is extremely very well understood. And like greedy algorithm, we know finds the minimizer of the function, which is kind of makes sense. Now it sort of makes sense that greedy works. Greedy prune would work for attractive models. So are we done in analyzing attractive models? Almost. There are a couple of caveats which are somewhat technical to address, but you have to work through them. One is that we don't have exact conditional variances. We have only estimates for them. So you have to make sure that your estimates are good enough without using too many samples. And the second one is that you have to argue that somehow if you miss a vertex, you will be noticeably away from optimum. And that every vertex in your neighborhood is actually relevant. And this takes a little bit more work. But both of these are more technical than like conceptual hurdles, I'd say. Okay. So I think in the interest of time, I won't be able to go into too many proofs of our other results, but let me tell you proof of the supermodularity result, which I think is very nice. The original papers had somewhat different proofs, but here's a simple linear algebraic proof. So let me normalize the precision matrix so that the diagonal entries are 1. And normalization doesn't change the supermodularity, so it suffices to prove supermodularity of the conditional variance function under this normalization. And you use the determinantal formula and some linear algebra to see that this is true for any model actually, that the conditional variance of x1 given xs is exactly the number of paths. Actually, this I should be 1, but the number of cycles in your graph. If you take a cycle in your graph that starts at 1, ends at 1, but does not touch any vertex in S. And for each such cycle, you take the product of the edge weights with their negative sign. Okay. So for each cycle starting at 1 and ending at 1, which doesn't touch S, you take the product of the edge weights. And if the model is attractive, then each theta ij is negative. So negative theta ij is positive. So you're adding a bunch of positive numbers here. So the difference between f of s and f of s union j is the sum on cycles that touch the vertex j but don't touch the set S. And clearly now, if I take a bigger set S, bigger set T, the set of cycles you're summing over is smaller, right? So the condition is that you should not touch S. There are fewer cycles which do not touch T compared to do not touch S. So you're taking a smaller sum, so supermodularity would follow. Okay. So this is the proof of supermodularity. Now let's go back to walk summable models. And here the conditional variance function, which is again the same function that we see used in our greedy algorithm, is no longer supermodular. And it is not even weakly supermodular under various notions of weakness, which were studied and were known to suffice for greedy optimization, but it doesn't satisfy any of those guarantees. So why does greedy work even though the function is not supermodular here? So the analysis kind of has two steps. First, we reduce to the case of symmetric diagonally dominant matrices, something that are easier to study. And once we go to SDD matrices, we show some structural results, and the most important of which is that every neighbor would have a noticeable effect on your conditional variance. So let me elaborate on these in the next 2 minutes. So the first result, first before talking about them, I need to define what SDD matrices are. And a matrix theta is SDD if the diagonal entry is bigger than the sum of absolute values of the entries in the row, of the remaining entries in the row. And any symmetric diagonally dominant matrix is PSD. And there's this very nice observation from 2009 that, or maybe even earlier in some folklore results, that if a matrix theta is walk summable, then there is a diagonal scaling of theta such that the resulting matrix is symmetric diagonally dominant. And since the greedy algorithm actually is scale invariant when you do diagonal scalings, showing it works for walk summable matrices is equivalent to showing it works for symmetric diagonally dominant matrices. So we can focus our analysis just on SDD matrices. Okay, so let's now go to SDD matrices, and the main punchline of the analysis is the following lemma. Which gives a bound on the conditional variances. To state the bound without much notation, let me make one more normalizing assumption, which is that the diagonal entries of my theta are 1. Okay, and if you don't have this, you just have to scale the final bound appropriately. But if you have this, then the kappa condition becomes something very nice. It says that every non-zero entry in my precision matrix is at least kappa in absolute value. Okay. And the main technical lemma we have is that if your theta is SDD, symmetric diagonally dominant, and satisfies this normalization, theta is 1, then the conditional variances are all bounded. That is, take any two adjacent vertices I and j, then the variance of xi given xj is independent of the dimension p. In fact, is at most 1 over kappa. Okay. And this is very nice because without the conditioning, the variance could be very large. Even when theta is 1, the variance could be as large as p. For instance, if you go back to the random walk model, the variances were growing with I, the index I. In particular, the vertices in the last half would have variance which is omega p. Right? Whereas all of the conditional variances are always just 1 because you're adding exactly one additional Gaussian. Okay, and this is not true. This bound that variance of xi given xj is small is not true for general sparse precision matrices, even when you have this kappa guarantee. Okay, and why is this useful? So the main problem with the earlier methods like Glasser and Klein was that when you look at their analysis, they need some assumption saying that the variances of xi are small relative to the entries in the precision matrix. But now we are saying, okay, that might have been false to begin with, but if I condition on one neighbor, then you're kind of in the good, well-conditioned case. Once I condition on a neighbor, the variances are all very small, 1 over kappa. And we can exploit this to kind of use the earlier algorithms after finding one vertex. And this can be done with few samples and so on. Okay. So that's all I wanted to say in terms of proof, but just as a plug, just as a hint rather, towards the proof of this statement, we reduce this proving the statement for SDD matrices to proving it for Laplacian matrices, graph Laplacians, and there this inequality follows from some application of triangle inequality for effective resistance metric, if you know what they are. Okay. So that's all I wanted to say about the analysis. And in summary, the main challenge that we talked about was that of learning GGMs, degree D, pairwise correlation is kappa, and we want runtime, which is p to the little o of t. I don't want to enumerate all possible neighborhoods. And can you get sample complexity that is, polylog p? I'm allowing you, let's say even arbitrary dependence on d and kappa, but you should really be able to do poly d, poly 1 over kappa. And the problem is very well studied, it's practically important. And today I describe some algorithm, a greedy algorithm which solves the problem, some interesting special cases. Okay, but let me skip this bigger picture. We've seen many of that already. And there are many questions for GGMs that are open. So the main question I'd say is, are there other, classes of models that we can solve? Even testing is completely unknown. If I give you a GGM, if I give you samples from a GGM and I tell you, okay, here's my graph G, tell me whether this graph G is the right one or not. We don't know how to solve it. What happens if I have a GGM, but now there's an additional aspect that some variables are hidden. I'm missing some observations. And finally, given that the general GGM problem seems difficult to solve, is there some reason, some gap? Is there some computational versus statistical gap here? And I actually think that the general problem is hard. My belief is that there is no something like p to the little of the algorithm to recover the structure for general GGMs with sample complexity that is polylogarithmic in the dimension p. I'd be happy if you prove me wrong, but that's, I think, where the complexity stands. Okay, so let me stop with that.
Cool, thanks, Raghu, for a very interesting talk. Do people have any questions?
Yeah, it's a great talk. Sorry, I have some questions. So like Climb and like a variety of other sort of structural learning problems, they usually start with, I want to minimize I want to optimize some function, subject to this constraint, and then it goes about solving it, right? Did you have such an optimization, like does your greedy algorithm is a solution to a particular optimization problem?
That's actually a very good question. I don't think we have that. So in some sense, yeah, I don't have a good answer to that. I don't think we have a single optimization problem solving which would give us this. It's just kind of weird, right? Because you could have thought of OMP itself, orthogonal matching pursuit, which is our algorithm, as one way to solve the lasso objective, right? But if you start with that as your optimization problem, then that doesn't work. But the algorithm that people use to solve that optimization problem somehow works.
Right.
Right. So it's, yeah, I don't have a good objective problem, good optimization question solving which would work here.
I see. Thank you. Could you repeat the pruning step? Because I didn't understand the pruning step.
Sure. So the pruning step basically checks, where did it go? Yeah, it should be here. Right, so you have your set S. Now for each vertex in this set, you drop that vertex and see if the conditional variance has increased by more than, let's say, 1.01 factor. So when I drop it, the conditional variance could increase, and if it increased too much, then you don't drop it. But if it didn't increase too much, meaning it didn't change when you drop the vertex, you drop that vertex and go on.
I see. Yeah, thank you.
And how do you choose tau?
Tau is actually chosen based on, in the paper we kind of have a formula for it. I definitely don't remember it offhand, but it's something that depends on the degree d and kappa. You need to have some upper bounds on them to make this equation work.
Have you guys tried running your algorithm on some data sets? Sorry.
So let me answer Guy first. So yeah, definitely we tried it on, Freddie tried it on some examples, and basically it seemed to work pretty well. And one of the things that we tried actually was to see how realistic this walk summable assumption was. And for this, Freddie pulled out some, some networks that arise in gene regulatory networks, and then checked if they were close to being walk summable. And surprisingly, they were reasonably close to being walk summable under some notion of closeness, which is pretty interesting. So I'd say maybe that's some evidence of that this could be useful in practice.
Yeah.
Yeah, so could you elaborate a bit on the conjecture you made in the last slide?
Right, so let me go back. So the conjecture is basically saying that if I give you general samples from a GGM, we know that d log p or kappa squared samples suffice information theoretically. And there is a p to the d algorithm where you kind of enumerate over all possible neighborhoods. And my conjecture, or maybe I should even just say question, but my conjecture is that there is no p to the little o of d algorithm, which would recover the dependency graph, given only polylogarithmic in p samples, and the dependence on degree d is d, polynomial in d and polynomial in 1 over kappa.
Gotcha, but you don't. It's not like you have a specific argument in mind, or at least.
No. I mean, I wish I had. It's not even. This is a problem where the complexity, I think, is kind of even more open than many other problems, because we don't even have any sort of potential hard instances. It doesn't it's not clear what would be a hard GGM. We've been trying to come up with hard instances, and then we came up with algorithms to break them and so on. So I don't have anything more concrete than this, and the fact that we tried to solve it for some time.
Thank you.
But I'm confused about your conjecture a little bit, because we don't even know if it's hard, with a improved dependence on 1 over kappa, right?
What do you mean? Yeah, so this is a stronger conjecture than we don't even know if we can do it with d log p or kappa square samples. I definitely agree. So this is kind of the most general and strongest conjecture you can make. Right, but I'm saying, either you'd get something like this or nothing.
Yeah, it's just there are weaker conjectures you could first have.
Yeah. Yeah. I mean, I know, but since there's so much ambiguity, might as well make the strongest conjecture.
Okay, fair enough.
Awesome. Well, thanks to both of our speakers this morning, Noak and Raghu. The next talk starts in 6 minutes, and Eric Price will tell us about some interesting new results on learning trees. So I guess feel free to go to Gathertown if you want, or get some tea.
All right, I'll get some coffee.
Exactly, yeah. So see you all in a few minutes.